Alright, so we're going to be dissecting the DeWalt DCF815 impact driver and taking a look at the specific subsystems and seeing what really we're dealing with. So the first subsystem that we're going to be looking at is going to be the motor, the electronics, and then ultimately the battery pack. So the main function of this subsystem is to provide the energy and power for the impact driver to be able to perform the task. So the battery pack is connected down here at the bottom of the driver, and it provides the current which flows through the system up to the switch. The switch then provides current depending on the position of this switch up at the top to determine whether current doesn't flow through, it does flow through in one direction, or flows through the opposite direction. When the user pulls on the trigger, it closes the circuit, allowing electricity to flow through. So when the circuit is closed and current is running through, you'll see that there are two different directions that the wires go to allow current to flow. One direction actually brings current over here to where it connects to the LED source, which provides light for the user, and the other direction of current provides the energy for the motor. The motor is important because it converts our electrical energy into mechanical energy. This mechanical energy then actually rotates the gears and ultimately is what causes our impact driver to rotate and get the job done. So the specific components for this subsystem include the battery pack, the switch, and ultimately our motor. So starting off with the battery pack. The battery pack is going to be something that's vital to our system because it provides the energy for the impact driver to actually function. The energy from the battery is transferred through the system and ultimately converted from electrical energy to mechanical energy in the motor. The battery is rechargeable, so it can be plugged into a wall outlet when it runs out of power and then reused again and again. The battery just slides simply into the bottom of the driver, locking into place. This constraint is important because it keeps the battery in place on the impact driver when being used. So that way, the battery doesn't fall out in the middle of use. Another important factor in the structure behind the battery pack is the flat bottom, which allows for the flush placement of the drill directly onto the surface without tipping over. Another component of the subsystem is going to be our switch. The switch allows the user to open or close the circuit to allow current to be supplied to the motor and the LED. It also allows the direction of the current to be switched, which ultimately will change whether the motor spins clockwise or counterclockwise. This allows for our driver to both insert objects as well as take objects out. The switch is very important because you can lock it so that the switch will not close, so that no energy will be sent to the motor to ultimately turn the driver to spin. This is important because when the user is not paying attention and not directly using the tool, you don't want it spinning and potentially causing harm to the user. The switch is constrained by the housing so that it fits in flush and stays in place. All of the electronics inside of the switch are enclosed in this black plastic casing. The rest of the circuitry is all enclosed within the housing with strategic passages and channels that were made for the wires to slip in with ease. The motor provides the transfer from electrical to mechanical energy. The current enters through the back of the motor and begins the rotation of its internal components. As the inside of the motor rotates, the axle protruding from the front also rotates as well, in turn rotating the gears of the impact driver and ultimately causing the bits to spin. The axle is inserted directly into the gear towards the front of the tool and is constrained to move with the gears. It is only allowed to rotate on this axis and not translate forward or backward. As for the constraints with the motor itself, the internal components fit nicely into this motor housing, and the plastic shell of the body of the drill provides a nice fit for the motor housing, which isn't too tight to provide the space needed to allow the heat to properly be expelled around the motor housing without affecting the tool. The next subsystem is the Housing, Physical Switches, and Ergonomic Features subsystem. The main function of the housing is to hold the components on the inside and protect them. The components on the inside actually have very little structure. The housing provides a tight fit for the components to keep them in place. With the components locked in place, the weight distribution throughout the tool is very important. The weight distribution affects where the center of gravity of the tool will be. The position of the center of gravity is important because it affects the moment about the user's wrist. The bottom of the body, where the battery is attached, has a larger surface area for this impact driver. This allows for the tool to stand up on its own when the battery is attached, which provides a lot of comfort for the user to not have to worry about setting it down. The switch that's included above the trigger is there for the user to determine the direction that the impact driver rotates. It can also be used to stop all current altogether, to act almost as a safety to protect the user from the tool going off when it is unwanted to be used. A force on either side of the switch will move the motor into forward, reverse position, or locked. Some of the ergonomic features of the drill include the light weight of the tool and the slick handle design. The tool is made to be operated with only one hand, meaning that grip is very, very important. The handle is designed in such a way that it is the correct size to comfortably fit within your hand, and includes rubber for added grip and comfort. There are many parts of the housing that are designed specifically to accommodate the functions that were discussed previously. The top of the body houses the motor and hammer, which make up a majority of the weight of the tool. The top length determines the weight distribution in the x-axis. More weight in the front or in the back could increase the moment about the user's wrist. The height of the body affects the moment and the user's wrist as well. When the tool is in operation and the bit is facing downward, the weight distribution about the height of the tool is important to design for. The bottom of the body has a larger surface area, so when the battery is attached, it can be stood up on the end. The handle is designed in a way to fit comfortably and provide grip. The switch can be modified by applying a force to either side, causing it to move and change the internal structure of the tool. The trigger is designed into the body in a way that it can be easily pressed with the user's finger in a comfortable position. The spring is held in place behind the trigger to resist movement, meaning that when the tool is not in use, the trigger is being forced all the way out, and therefore the motor is not running. Lights surround the drill bit come on when the tool is in use. These lights shine forward to illuminate the area that is being worked on. Now looking to the subsystem characteristics. Each of the dimensions for the shell are important. The size has to be large enough to fit all of the internal components, but arranged in such a strategic way that their center of gravity is the most convenient for the user. The length of the top portion of the body strongly affects the horizontal position of the center of gravity. The height strongly affects the vertical position for the center of gravity. The width of the base has to be large enough to support the tool for it to remain upright position when placed down. It is important to note the position of the center of gravity in relation to the base surface area to understand how much of a moment the impact driver can withstand before falling over. The width and contour of the handle is important because each curve and distance must be comfortable for the user. The user has only one point of contact with the tool, so grip is going to be very important. The material properties that are important are the thermal conductivity of the various materials. This was discussed in the thermal management subsystem section, but applies here as well. The housing is a very precise size and shape, and the heat could alter these. The grade of the plastic, the thickness of the rubber, and the conductivity of the aluminum are all very important factors to continue. The user is applying a force to the trigger. There is only one finger involved. The force applied has to be large enough to compress the spring behind the trigger, meaning that spring stiffness is an important factor to consider. A spring too stiff will mean difficulty for the user to press the trigger, but a spring that's not stiff enough will mean that the user will have much less control over the speed they intend for the tool. A light force could also press the trigger all the way down, causing the tool to run full speed when it might not be necessary. The position of the lights have to be in such a way that the output is helpful for the user. The light strength is also important to consider. The lights need to be strong enough and also in a position that's actually useful. Position above and behind the trigger that the direction switch is located is important when attempting to quickly change directions. The switch has to be positioned in a spot that the user can reach easily, preferably with the hand that is already on the handle. The stiffness of the switch is also a very important value. The force needed to change the position depends on the stiffness of the switch. Because there are 3 positions the switch has to go, it has to be stiff enough that the user can tell the appropriate setting for the switch, but not too stiff that they can't actually push it. The force required should be able to be generated with just one finger, the most common way that users will interact with the switch. One very important subsystem to the impact driver is the thermal subsystem. The main function of the thermal subsystem is to release heat in a manner that does not affect the tool or the user. When the motor is running, heat is generated. Finding a way to dissipate that heat is very important for the function. Increased heat can lower the performance of the motor. The function is also to have the heat leave the tool in an area that won't affect the user. The heat can raise the temperature of the rubber and the plastic of the tool where the user is holding. Preventing the user from getting burned or holding a tool that is uncomfortably hot is very important. Materials used and location of components is the most important part of defining the function of the thermal management subsystem. There are several components that are important to the thermal subsystem. One of these is the motor. Heat inside the tool is mainly going to be generated from our motor, meaning that heat is directly affecting the upper body of the tool. Inside of the motor is a fan that expels the heat from the holes that can be seen on the left side of the motor. Another component is the body. The body is mainly composed of plastic and rubber. The plastic is great for the strength of the tool because it isn't very flexible, meaning the tool will be supported. The rubber on the inside and outside of the tool is used for comfort for the user or for additional support. There are holes cut out in the body where the motor is going to be expelling the most heat. The holes are large enough to expel the heat, but not large enough that the user could accidentally insert an object or a finger or something to get in there to hurt themselves. Next to the holes, there's a rectangular section of rubber. This rubber is useful when the tool is placed down on its side, so that the raised rubber allows the tool to be set slightly off the surface, meaning that heat can expel on the side without going directly to the surface. The heat can get trapped inside the shell and disperse all over, meaning the temperature would gradually rise in the handle while the user is holding it. So it's important that this handle is made out of rubber to be able to provide the user a comfortable spot to grab that will not get too hot. Another component for the thermal subsystem is going to be the nose cone. So inside of the nose cone, we have the impactor, which is constantly moving, and it's generating a lot of heat at the front of the tool. Unlike the rest of the tool, the nose cone is actually made of aluminum. The aluminum accepts a lot of the heat and acts almost as if it's a heat sink. This prevents the tools from melting or deforming under the extreme heat. The last component is going to be the circuit. The flow of electricity through this tool can be seen mostly in the center, towards the handle. This electricity will actually cause an increase in temperature. The large metal plate acts as another heat sink, accepting a lot of the heat instead of transferring it to the plastic or rubber that the user may be in contact with when using the tool. As the temperature rises, the resistance is also increased. In the circuit is a thermistor, which has a variable resistance based on the surrounding temperature. The tool will eventually shut off if the temperature gets too high, as a safety precaution for the user. One of the thermal subsystem characteristics is heat. Heat is inevitable in this scenario, meaning the main thing to account for is the temperature and location of where the heat is in the tool. There are various ways to manage these things. Conductivity of materials is a very important factor to keep in mind when designing. Weak material could allow temperature to pass through very easily, making it dangerous, and strong material might not be as lightweight or cheap. It is important to know the conductivities of the plastic, the rubber, and ultimately the aluminum. Heat being expelled is a must to keep the tool from overheating, but you can't just have the motor exposed. The motor being exposed can be dangerous for the user. The ventilation has to be large enough to transport the heat and in a direction that forces the heat away from the user. The distance behind the tool that the heat is being expelled is also important. The heat is being expelled from the motor at a specific rate relating to the motor. The fan speed inside the motor will give us information about the amount of heat that is being expelled and at what rate. Understanding the temperature distribution throughout the tool is important for knowing where to place the rubber. Certain temperatures may be deemed dangerous, and more plastic or rubber will have to be used in that area. The exact values of the temperatures throughout the tool is important to know to see if there are more thermal management that's needed to do in order to keep the tool at a reasonable temperature and safe for the user. The final value that is important is the sensitivity of the thermistor. Managing the outer temperature can be accomplished with regard for the internal portion of the tool. It is vital that the maximum safe temperature be found and a thermistor used that will prevent the tool from operating above that threshold. A thermistor that is too sensitive will cause the tool to shut off too early when the temperature is not even that high. A thermistor that isn't sensitive enough will allow the tool to get too hot before shutting off, potentially damaging parts of the tool or the user. Our next subsystem is the bit retention system. The bit retention system's main function is to be able to accept and release a bit, hold the bit securely, and transfer torque from the tool to the screw. Different screws and different bolts will require different bits to be used, so it's important for the bit retention system to be able to insert or remove the different bits. It is also important that the impact driver be designed in a way that it's very easy for the driver to insert or remove a bit while still holding onto the bit securely. The bit, once inserted, is then held in place by a ball bearing system. The ball bearing prevents the bit from having any unwanted translational movement. The hexagonal design of the sleeve prevents the bit from any unwanted rotational movement that's not caused by the motor of the impact driver. The components of the bit retention system include the anvil and the housing. The anvil is impacted on by the internal impacting system. Once impacted, the bit rotates and translates the torque from the tool to the screw. To the right of the housing is where the bit is inserted. There's a hole in a hexagonal shape that matches the shape of the drill bits. The spring and ball bearing compress and allow the bit to slide in and lock into place. Another component is the bit release. Components included in this system are the washers, plates, spring, and a pin. When a bit is inserted into the system, the pin is forced down and compresses the spring. All of these components are located on the center of the anvil, with the pin facing the front of the tool and the spring between the motor and the pin. Another component is the collar and compression spring. Components included in this system are the collar, the compression spring, a washer, and a ring lock. The collar is the outermost part of the system. The collar has a rough texture, which helps the user create friction when attempting to remove a bit. This is done by pulling the collar away from the tool, which creates more tension in the compression spring, meaning when the user releases the collar, it will retract the force back into the spring. The most important subsystem characteristic of the bit retention subsystem is spring stiffness. The multiple springs throughout need to have very specific stiffnesses to ensure the forces are all balanced out and act properly. For example, the spring that's pushed down by the pin has to be strong enough that the outward force can hold the bit in place, but not too stiff to the point that it is difficult to insert the bit as far as needed to lock. Similarly, the spring that is inside the collar has to be strong enough to hold the collar in the back position, but not too stiff that the user can't pull the collar to release the bit. The spring whose job is to hold the ball bearing in place is also very important. The spring must provide enough force to hold the ball bearing in place when the system is supposed to be locked, but not so much that inserting the bit and compressing the spring is difficult. Other measurable characteristics involve the hole that the bit is inserted in. The standard bit has very precise dimensions, and the tool needs to be able to house these bits. The distance down the shaft and the ball bearing has to coincide with the divot on the bit. The last subsystem is the impactor and transmission subsystem. The impactor mechanism inside the impact drill allows the tool to generate large amounts of torque in a compact space. The motor provides constant rotation, while the impact mechanism is able to turn that into high torque with impulsive movements. The first step in this process is the motor. The motor uses the electric energy and transforms this into rotational energy. This motor is in a form of constant rotation. The motor is translated to the planetary gears. The planetary gears are then able to take the rotation being applied and slow down that rotation. The benefit of slowing it down is that there's now more torque that's being applied. The next step is the hammer to begin turning. The anvil prevents rotation motion after a certain point. When the rotational moment is being resisted, the hammer is then pulled back, causing the spring to compress. The spring compress causes the shaft to rotate. As seen in the shaft, there are diagonal ridges. These ridges hold ball bearings. Once the hammer's teeth reach the top of the anvil and the spring is compressed to its maximum value, the hammer skips off and the shaft begins to rotate. These rotations are the high torque impulse hits. The shaft is directly connected to the bit retention system, meaning the force is then being exerted directly onto the bit. The major components in the subsystem include the motor, which is important for driving the gears, and the planetary gears and gearbox. This part is also referred to as the transmission, where the gears are able to lower the speed and increase the torque. It can be seen that there is one main gear in the center of the system, Along the outside of this main gear are the two planetary gears, which are rotated around the main gear, but still inside of the gear ring. The gear ring is stationary and constrained in every direction, and provides a track for the planetary gears to flow during their motion. The planetary gears lower the speed and increase the torque, as compared to the central gear, which is output on the shaft and can be seen in the picture attached in the lab report. Gear ratios are important because these planetary gears are what are slowing the motion and raising the torque. Needing more rotations about the center of gravity means more torque but less frequent impacts. The gear ratio can be found by finding the ratios of the radii of the pin and the gear ring. The speed of the motor is not ideal for operation of the impact driver. By adjusting the gear radius or the radius of the gears, we can obtain the desired speed and torque. Related to the gear ratio is the RPM. The RPM of various shafts leading to the bit have different rotational speeds depending on their gears. Adjusting the size of the gear and shafts can allow us to control the output RPM, or how many times per minute the impact system is actually hitting and causing the screw to rotate. Using the gear ratio, we can find a relationship between the output RPM of the motor and the output RPM of the entire tool. Different motors will have different specifications and different RPM values. If there is a desired output RPM, we can find which motors are most suitable for our tool. When the hammer makes contact with the anvil, the moment of inertia determines how much force is being applied onto the anvil. This force value is important because this force multiplied by the moment arm gives us our torque value. The important values determining the moment of inertia are the mass and the radius of the hammer. The final characteristic that's important to the subsystem is the angle of the V-groove of the shaft. The angle of the groove determines how many rotations are needed before the hammer is pulled back far enough to skip over the teeth of the anvil. A lower angle means less rotations needed, meaning less energy is stored, resulting in less of an output of torque. A higher angle means more rotations needed, meaning more energy being stored in the system. When the hammer is released in this case, the torque output is going to be much higher. The more rotations take more time, meaning less RPM, but more torque. Depending on the job of the tool that's being used, these values will be important to the user who might need more torque. That's our final subsystem that we're going to be discussing with our video analysis. Feel free to read further into the lab report, and thank you for watching the video.